Unified Dynamics.
Hi, and welcome to this Unified Dynamics slide deck review. I'm Benjamin Mays, theory architect. Let's dive right into it. This opening slide frames the central translation problem. How do we move from abstract quantum information into thermodynamic language that traditional physics can evaluate? On the left, the blueprint represents the quantum side: entangled states, discrete graph structure, qubit representation, and entropy expressed through the density matrix. This is the mathematical language of correlation. On the right, the same structure is rendered as thermodynamic reality: heat transfer, work output, internal energy, exhaust pressure, and engine cycle behavior. The goal is not to claim that entanglement is simply hidden heat. The goal is more precise: to show how correlation structure can carry work potential under defined physical operations. In unified dynamics terms, this is the B2 bridge. We are translating admissible connectivity into thermodynamic consequences without overclaiming a completed gravity or unification proof. This deck is the blueprint for that translation. Moving along to the translation gap, we have the abstract quantum side: wave functions, probability clouds, interference, entanglement entropy, and von Neumann-style information measures. That math is powerful, but by itself, it doesn't naturally tell a classical reviewer where the physical heat, work, or energy exchange shows up. Then we move into the boiler room: thermal radiation, pressure, temperature, and physical work. This is the language traditional thermodynamics understands. The point of the 2026 quantum heat breakthrough is that this wall is starting to crack. We're no longer just talking about information in the abstract. We're starting to measure how quantum correlations interface with real energy transfer. So the key message is simple: the disconnect isn't a failure of physics, it's a translation problem. We've had the equations for entanglement for decades. Now we're building the units and vocabulary to connect those equations to work, heat, and thermodynamic reality. This next slide is the translation matrix, basically the dictionary between classical thermodynamics and unified dynamics. On the left, we have the familiar thermodynamic terms: pressure, temperature, work, and heat transfer. These are words traditional physics reviewers already trust. In the middle, we show the UD equivalent. Pressure becomes topological boundary pressure, informational stress pushing against a local capacity limit. Temperature becomes branch change, or the rate at which local connectivity reorganizes. Work becomes network informational stress, the system doing structural rearrangement. And heat transfer becomes holonomy mismatch, where broken or disrupted correlation structure produces measurable dissipation. The right column is the actual bridge. It explains how abstract quantum correlation can be translated into physical behavior: expansion, cooling, mechanical redistribution, and thermal release. The key point is not that entanglement is secretly ordinary heat. The point is that when structured connectivity is created, maintained, or broken under defined operations, it can have thermodynamic consequences that look like work, heat, and dissipation. Alright, so the idea here is to stop treating entanglement entropy as just an abstract information number and start asking what that structure can physically do. In the first frame, the system is entangled and stable. The connectivity is organized, and there's potential stored in the correlation structure. In the second frame, that bond is strained. The system is still coherent, but the connection is under stress, almost like a wound spring. In the third frame, the bond ruptures or decoheres, and that stored structure is no longer available as ordered connectivity. Under the right physical operation, that loss of structure can show up as measurable work, heat, or dissipation. The key point is not that every quantum bond is literally heat. It's that correlation structure can carry usable work potential before it thermalizes. UD frames this through the neutral packet threshold, S sub naught equals 43/7, as the minimal capacity cost for stabilizing a neutral K4 packet. Instead of asking classical thermodynamics to accept new language, we translate the UD packet grammar into terms it already understands. The 5 channels here act like a microscopic engine specification. First, rho sub I, burden density. This represents the local load, strain, or stored pressure inside the packet. Second, theta sub I, transport phase. This is the directional phase of motion, like the orientation of a piston stroke in an engine cycle. Third, chi sub I, closure branch. This tracks whether the packet closes into a stable loop, similar to flywheel rotation or holonomy closure. Fourth, sigma sub I, framing class. This represents the handedness or orientation of the packet's internal volume. And fifth, B sub I, boundary integrity. This is the gasket condition, whether the packet boundary remains sealed and admissible, or whether it begins to leak structure into the surrounding system. Together, rho, theta, chi, sigma, and B define the 5-channel packet state. So the point is simple. This is not just abstract symbolism. It is a proposed physical grammar for how quantum connectivity becomes thermodynamic behavior: load, phase, closure, orientation, and boundary control. This slide introduces the Pashner-Carnot cycle, a way of describing topological phase transitions using the language of an engine cycle. Stage 1 is intake. The packet accumulates burden, like an engine drawing in fuel or pressure. Stage 2 is the expansion valve. This is the 2 to 3 Pashner flip, where one compressed structure opens into a larger configuration. In thermodynamic language, the system is relieving pressure by expanding its available topology. Stage 3 is exhaust. The system vents excess strain as heat, dissipation, or lost coherence. Stage 4 is crystallization or compression. This is the 3 to 2 flip, where the structure contracts back into a more ordered state, similar to a compression stroke. The key idea is that topological rearrangement is not just geometry changing shape. In this model, the rearrangement performs thermodynamic work: intake, expansion, exhaust, and compression. Now, connecting open quantum dynamics to thermal cooling, the white curve shows co-frame density relaxing over time. At first, the system is highly ordered and highly burdened. Then, as time passes, that structure decays toward a lower energy state. The sharp drops mark critical Pashner flip events. These are moments where the network reorganizes its topology, sheds strain, and releases stored mismatch into the surrounding system. The thermal background shows the same idea in heat language. As the network loses processing debt, the thermal signature fades. In other words, the system cools as correlation stress is dissipated. The Lindblad connection is important because it gives reviewers a familiar framework: relaxation, decoherence, and irreversible loss of ordered state structure. In UD terms, this is the vacuum-shedding co-frame mismatch until it approaches equilibrium. Here, m is the number of saturated edge burden units loading a single vertex. It is not mass itself, it is the local packing count of how much burden the vertex is being asked to route. On the left, we're below the threshold. At m equals 10, the local packet is near capacity, about 95% loaded, but the structure is still transmitting. The system is strained, but it has not failed. On the right, we cross the critical point. At m equals 11, the local burden exceeds the vertex information capacity limit. C vertex equals 7/768. In UD language, that means the local routing channel can no longer remain admissible. So the horizon is interpreted as a quarantine boundary. Edge transport effectively shuts down, impedance spikes, and the overloaded region is isolated from the rest of the network. The key point is not that this proves black hole physics is solved. It's a B2 bridge, a proposed mechanism for how finite information capacity could produce horizon-like behavior and prevent runaway desynchronization. This next slide shows the proposed unit conversion pipeline for translating a dimensionless UD horizon count into Bekenstein-Hawking-style entropy language. On the left, we start with the topological input, a dimensionless constraint shown here as the overlap deficit, delta equals 7. By itself, that is not yet thermodynamics. It is just the discrete structural rule. In the center, the machinery converts that structure into an adjacency count on the horizon. The key move is counting independent edge or carrier states relative to a Planck scale area unit. On the right, that count is translated into the familiar Bekenstein-Hawking form, where entropy scales with horizon area. The careful point is this: we are not claiming the full black hole entropy derivation is finished here. This is a B2 bridge showing how a discrete carrier count could map into the area law structure reviewers already recognize. Let's look at how the discrete UD machinery starts to look like smooth macroscopic geometry. On the left, channel A is delta 0, which we're mapping to the tetrad or Vierbein side, basically the local frame that lets geometry become measurable. On the right, channel B is delta 1, which maps toward the spin connection, the rule for how those local frames rotate or transport from place to place. The middle is the important bridge, the structural Palatini correspondence. In standard relativity, Palatini methods separate the frame and connection. UD is proposing a discrete version of that split, using co-boundary operators instead of assuming smooth spacetime from the beginning. The graph shows the relaxation behavior, torsion and non-metricity decay toward a stable coarse limit, while curvature remains as the macroscopic geometric signal. So the careful claim is, general relativity may emerge as the relaxed coarse isotropic limit of the discrete packet machine. This is a B2 bridge, promising, structured, but still not a full GR proof. This slide reframes space itself as a thermal state, not just an empty container. Across the three panels, we're looking at the same mass defect at increasing resolution, level 3, level 5, and level 7. As the resolution tightens, the contraction limit gets smaller and the defect becomes more sharply localized. The key idea is that what we experience as smooth space may be the cooled, averaged out result of deeper network activity. At coarse resolution, the burden spreads out. At finer resolution, the system resolves that burden more precisely, and the the surrounding field looks more structured. In UD terms, distance and gravity are being treated as possible macroscopic bookkeeping effects of constrained connectivity and thermal relaxation. The careful claim is not that gravity is fully derived here, it's that spatial geometry may emerge from a cooling process, where the network sheds processing debt and settles into a stable large-scale thermal pattern. We move from concept into falsifiable telemetry. First, the genesis boundary. The simulation reaches n equals 7 and confirms a topological closure rate of about 94.07%. That means the system is hitting a measurable structural boundary, not just producing a visual pattern. Second, the ground state energy is E sub gs equals nu naught times F sub IFS to the 7th power. Numerically, that gives approximately 0.012594 electron volts. Third, the equivalence lock is lambda equals E sub gs to the 4th power. The point is that the vacuum scale output is tied to a 4th power energy relation. So the careful claim is this: the F6 simulation gives us a parameter-constrained B2 bridge from substrate closure to ground state energy to cosmological constant scaling. It's not final proof of cosmology, but it is a falsifiable numerical pathway. This slide is the big picture synthesis, the universal cooling law. We're moving from micro to transition to macro. On the left, the system is hot, dense, and highly structured at the packet level. In the middle, that structure starts reorganizing, shedding mismatch, releasing strain, and moving through transitional geometry. On the right, that process settles into the smooth macroscopic world we experience as space, distance, and gravity. The key idea is that geometry may be the cooled output of deeper quantum information dynamics. Gravity, in this framing, is not being declared solved. It's being modeled as a possible thermodynamic exhaust, the large-scale effect of information structure relaxing toward geometric equilibrium. So the message is simple. From the Planck scale boiler room to the continuum, UD is proposing one connected engine: correlation, cooling, and emergent geometry. So, quick recap. On one side, we have quantum correlation and entanglement. On the other side, we have pressure, volume, work, and heat. The goal is to show how abstract entanglement structure can be read in thermodynamic terms without pretending that information is automatically heat. Hidden heat is random kinetic variance inside a local reservoir. Entanglement, in this UD framing, is admissible connectivity, structured correlation that can preserve purity and carry potential without immediately becoming local thermal noise. The F6 Genesis run reports a closure rate of about 94.07% at level n equals 7. The ground state expression, E sub gs equals nu naught times F sub IFS to the 7th, means the vacuum energy scale is being filtered through 7 layers of IFS contraction. Von Neumann entropy, state vectors, and decoherence rate are translated into UD ledger terms: topological debt, carrier state, and boundary integrity. Then those are translated again into thermodynamic terms: capacity bound, microstate variable, and dissipation or heat exhaust. Rho sub I means burden density, or stored strain. Theta sub I means transport phase, or direction of exchange. Chi sub I means closure branch, or loop completion. Sigma sub I means framing class, or orientation. B sub I means boundary integrity, or whether structure leaks. Here the system is described like an engine. First, burden accumulates. Then a topological flip expands the structure and redistributes strain. Next, excess mismatch is exhausted as dissipation. Finally, the packet returns toward a recovered ground state. The point is that topology can behave like a work cycle. The 2-tetrahedron state becomes a 3-tetrahedron state, adding connectivity and redistributing stress. The equation, sigma peak 2 becomes sigma peak 3, means peak local strain drops after the flip. In plain terms, geometry acts like a stress relief valve. This is the smoothing argument. Asymmetric expansion spreads burden across 3 faces using a 4/3 multiplier. Symmetric consolidation then locks structure with a 3/2 multiplier. The takeaway is that structured geometry can smooth correlation flow before it degenerates into uncontrolled thermalization. Smooth geometry, written as M with metric G mu nu, is the macroscopic shadow of discrete capacity accounting. The vertex capacity limit, C vertex equals 7/768, means local information density has a finite routing ceiling. Kappa equals 1/9 pi squared is treated as a structural coupling candidate, not physical G. The meaning is simple. Curvature may reflect how the system preserves cycle reversibility under combinatorial saturation. The event horizon is framed as a surface where internal transport is cut off and carrier states are counted at the boundary. The Bekenstein-Hawking expression means entropy scales with horizon area. The safe claim is carrier count mapping, not a completed black hole proof. The 7-channel split is 1 + 5 + 1, 1 stable mode, 5 active fluctuation modes, and 1 residue kernel. The equation, active energy plus residue equals the original total, means capacity is conserved while active trace decays into stored residue. Matter patterns are shown as integrating smooth smoothly and reducing network stress. Antimatter patterns are shown as higher friction paths. The safe interpretation is not proof of baryogenesis, but a candidate thermodynamic sorting mechanism. First, classify the microgeometric correlation. Second, test whether the cycle preserves capacity. Third, ask whether macroscopic curvature reflects the underlying work potential gradient. This is the peer review bridge. Every abstract claim must pay its thermodynamic receipt. And finally, falsifiability. The next targets are larger F6 simulations and cosmological comparison tests, including B-mode polarization surveys. The final message is that the universe may not be a passive continuous sheet, but a capacity-limited information engine. The ledger is open for review. For current devlog and simulation evidence, head to udphysics.com.
Don't forget to like, subscribe, and share. And keep questioning reality.